Hello everyone. In this video we are going to check the frequency response of two first order compensators, which are the PI and lag compensator. These two compensators will be mainly used to improve the steady state behavior of the system, as we had them used for the same reason, for the same purpose, in the root locus design approach. So let's have a look at how the PI and lag compensator will be in terms of their amplitude and phase, and how they affect the frequency response of the whole system. Let's start with the PI controller. For the PI controller, we can say that for GCS, we have S plus ZC over S. Or we can write it in the form of S plus 1 over Ti over S. And we see that there is a 0. ZC is at minus 1 over Ti. And we have a pole at the origin, or 0. GC j omega will take the form of 1 over j omega times j omega plus 1 over Ti. And alternatively, we can write this in the form of 1 over Ti times 1 over j omega times 1 plus j omega Ti, omega times Ti. And again, we have the 0 at the same location, minus 1 over Ti, the pole at the origin. And we are now ready to draw the amplitude plot and phase plot for this controller. Amplitude of GC j omega will be equal to 1 over Ti times 1 over omega times the square root of 1 plus omega squared Ti squared. We can start to draw it. There are indeed 3 components. For the first component, we will have a constant value, 1 over Ti. For 1 over omega, we will have the, if we assume that omega equal to 1 is here. For this component, we will have a straight line with minus 20 decibel per decade as the slope. For the third component, which is the 0, amplitude is equal to square root of 1 plus omega squared Ti squared. At very low frequencies, we will have 0 dB or 1. At omega equal to 1 over Ti, we will have the corner frequency, and then after that frequency, we will have plus 20 dB per decade as the stop. And we have the third component, which is 1 over Ti. And for that, we will have some, depending on the value of Ti, we will have it as a constant value. Now we need to add all these to each other, and then we will get the, indeed the complete response. If we add them to each other, the amplitude plot for the PI controller with the transfer function that we have given, here we have omega, amplitude of GC j omega. So here we have 0 dB. Indeed, I think I need to redraw the part for 1 over Ti. We know that Ti will be a kind of big value, so 1 over Ti, which is the location of the 0 of the controller, will be close to the origin, so it will be much smaller than 1. And as a result, the amplitude that we get for 1 over Ti will be negative in terms of the decibel. So this will be somehow 1 over Ti. Of course, the exact value for this will depend on the Ti. But on the other hand, for the 1 over omega, at the frequency of at omega equal to 1 over Ti, we will have amplitude of 1 over omega being equal to Ti. Therefore, if I consider the two components together, 1 over Ti times 1 over omega, the amplitude at omega equal to 1 over Ti will be equal to 1 or 0 decibel. So therefore here we will have, at this frequency of 1 over Ti, we will have Ti as the value. And we can convert it into decibels, of course. Or we can say that it's equal to 20 logarithm of Ti in terms of decibel, and here we will have 20 logarithm of 1 over Ti, which is the minus 20 logarithm of Ti. And as a result, up to that frequency, Ti, at that frequency indeed, we will have 0 dB, but before that, we will have the slope of 1 over the slope of minus 20 dB per decade. After the frequency of 1 over Ti, the slope will become equal to 0 and the amplitude will remain at 0 dBs. And we assume that 1 over Ti is much smaller than 1. So this will be indeed the amplitude plot for the PI controller, where we have Gc of j omega, or S, being equal to j omega plus 1 over Ti over j omega. That's the transfer function that we have used. And you can see it again over here. Of course, if you have a proportional factor or gain factor, such as K, this K will move the amplitude plot up or down, depending on the value. But without that K, we have the amplitude at very high frequencies equal to 0 dB. At very low frequencies, we will have the slope of minus 20 dB per decade. And in this way, we will increase the type of the system, the steady state behavior of the system will improve, but the transient behavior of the system will remain the same because we are not going to change it. And it will be obvious when I draw the phase plot for this. So phase of Gcj omega will have two components. One which comes from the pole at the denominator, at the origin, will be always equal to minus pi over 2. On the other hand, for the 0 that we have, and for 0 we have S plus 1 over Ti, where 1 over Ti frequency is over here. For that one, since it's a 0, at 1 decade after 1 over Ti, the phase will become pi over 2. 1 decade before that, the phase will be 0, and at that frequency we'll have the pi over 4 as the frequency, and therefore the approximate phase will be like this. Now to obtain the phase plot for the whole controller, we need to add these to each other. 1 decade after 1 over Ti, the phase will become 0, and initially it will be equal to minus pi over 2. And again, we assume that 1 or 1 over Ti is much smaller than 1. So what you see in black is the final phase for GCJ omega, where we have the controller in the form of a PI controller. Now, especially if the crossover frequency for the gain is much bigger than 1 over Ti, in this case if it's bigger than 1, then we see that the phase contribution of the controller will be 0. The gain contribution will be 0 dB as well. Therefore, that part of the body plot for the whole system will remain the same, while at the very low frequency we will increase the amplitude quite a lot. We will add this slope of minus 20 dB per decade. And as the frequency gets smaller and smaller, the amplitude gets bigger. Indeed, the type of the system is increasing. And we are injecting some negative phase, but since it happens at the very low frequencies, it will be fine and it will not create instability problems, for example. For the PI controllers, the main thing would be to pick a value for the location of the 0 or 1 over Ti, the value for Ti. Usually we should pick it such that the frequency components or the phase and amplitude characteristics that we add to our system run the crossover frequency is equal to 0. And we just change the behavior of the system at the very low frequency. And you should keep in mind that we had a similar case when we were doing it using the root locus approach. We were placing 0 pretty close to the pole at the origin in order to keep the root locus plot or sketch of the system the same. In that case, the transient behavior would remain the same. Now the next controller that we are going to discuss is the lag compensator. For the lag compensator, we can, first of all, you know that it will be used in order to increase the gain at very low frequencies and not touch the transient behavior. And this is similar to what we were doing in the root locus controller design approach. We were placing the pole and 0 of the controller pretty close to each other and pretty close to the origin. So we had the pole here and 0 here. They were very close to each other, very close to the origin, and therefore the overall shape of the root locus sketch was remaining the same. But depending on the ratio that we had between these two, between the pole and the 0, we were able to increase the gain at very low frequencies. So here we will have the controller GC of S expressed in the form of alpha times 1 plus S times T over 1 plus S times alpha T, where we have alpha bigger than 1. If you look at the amplitude of GCJ omega, it will be in the form of alpha times square root of 1 plus omega squared T squared over square root of 1 plus omega squared alpha squared T squared. So we can see that the amplitude of J omega at very low frequencies will be equal to alpha. Amplitude of G of J omega, GCJ omega, at very high frequencies will be equal to 1 or 0 dB. Let's draw the body plot for this controller. Here we have the amplitude and here we have the phase. So we have 3 components for the amplitude and 3 components for the phase. For the amplitude, we have the first one as alpha. So this will be the constant value which comes from alpha, 20 logarithm of alpha, and we know that it is bigger than alpha is bigger than 1. So this will be on the positive side in terms of the decibel. Then we have the pole appearing. The pole of the controller is P of PC is at -1 over alpha times t, while the 0 of the controller, ZC, is at -1 over t. So first we will see the pole and then we will see the 0. In terms of the amplitude, this will be what we are going to face. So at the frequency of 1 over alpha times t, we will have a corner frequency, 0 till that point, and after that we will have a negative. Since it's a pole, we will have -20 dB per decade. Then at the frequency of 1 over t, we will have another corner frequency, and we will have the 0, the amplitude for the 0 term with 20 dB per decade as the slope. And then we need to add all these to each other in order to have the amplitude plot for the whole system. Let me choose the black color. So up to omega equal to 1 over alpha times t, we will have 20 logarithm of alpha. Then we have the -20 dB per decade appearing. And after that, we will have the effect of the 0, and as a result, the amplitude will have the slope of 0 dB per decade, and its value will remain as 0 dB or 1, because that's what we already know that we will have. So this will be the amplitude plot for this compensator with the transfer function that I have provided. In terms of the phase, alpha will have no contribution, it will be 0 degrees. Then regarding the pole, which appears at -1 over alpha t, initially we will have 0 degrees. At that frequency, we'll have minus pi over 4. And finally, it will go down to minus pi over 2. So this will be the approximate phase plot for that system. For the 0, at the frequency of 1 over t, we'll have pi over 4. Finally, it will reach pi over 2 and 1 decade before, and after that we will have the difference as you can see here. And then we just combine these with each other in order to have the complete phase plot for the system. Finally, we'll reach 0. We start with the 0. The phase becomes negative. At some point, it goes back towards the 0. And again, we assume that this, since the pole and 0 of the controller are pretty close to the origin, this 1 over t and 1 over alpha t is much smaller than 1 over. They are much below the crossover frequency. And now you can see the effect of the lag compensator on the whole system. At high frequencies, or let's say around the crossover frequency, the controller will have no effect because its amplitude will be 0 dB, its phase will be 0 degrees. On the other hand, at the low frequencies, we will have some negative phase introduced to the system. And at the same time, we will have the amplitude of the system at the very low frequencies increase by this value, 20 logarithm of alpha. So this will help to improve the steady state behavior. At the same time, the transient behavior will remain almost the same, because since we don't change the body plot for the system around the crossover frequency, the phase margin will remain the same, the crossover frequency will remain the same, and as a result, the transient behavior will remain almost the same. So in designing the lag compensators, you need to come up with the value for alpha according to the design requirements. So it would depend on how much improvement you need to impose. how much improvement you need to bring with the compensator. So from there, you will obtain a value for alpha with this 20 logarithm of alpha. And then you need to pick a value for 1 over t. You should choose the location for the 0 of the controller much below the crossover frequency. So if you will have the flexibility over here. It's indeed similar to the flexibility that we had in designing the controller using the root locus, because over there we were able to pick the location for the 0 and then find the location for the pole. And here we have somehow a similar case. So we will find the exact value for alpha that we want to have, and then we will pick a value for 1 over t for the location of the 0 based on the body plot of the whole system without the compensator, such that we don't touch the body plot of the system around the crossover frequency by introducing this compensator. Once we have 1 over t and alpha, we will be able to find the location for the pole of the controller as well, and then we will have the controller designed. If we have the value for alpha and t, we will be done with the controller. Alright, so I think that's all for this video. I hope you have got how the PI controller and the lag controller will behave and how they will improve the steady state behavior of the system while not touching the transient response of the system. Thank you for watching and see you in the next video.